Okay, welcome back from the coffee break, everyone. Okay, our second talk for the morning and the second talk for the day is Christine, and she'll be giving her last talk on multi-graded modules. Okay,
right, thanks, Adam. All right, so let's recap where we're at. Right. We've been talking about multi-graded modules and how they correspond often to geometric objects in nice settings. In particular, we're thinking about simplicial toric varieties. And our hope is to use our understanding of multigraded modules and their syzygies to extract geometric information, right? Okay, so yesterday was Wednesday, yes, and we talked about multigraded regularity, right? And how, right, from we have three definitions of regularity for projective space that are equivalent. They're no longer equivalent, but if we pick one of them, the local cohomology one, then we could extract analogs of the other two in various ways, right? So we had quasi-linearity instead of linearity, and then we could pull virtual resolutions out of the minimal free resolution using, pieces of the regularity. So the free resolution isn't completely seeing the regularity, but it's not totally unrelated to it. Okay. So today I want to go back to Hilbert's syzygy theorem, right? Remember that restricts the length of a free resolution for a coordinate ring of a projective variety to the dimension of that projective space. And now I want to think about this setting. Right, so we have our simplicial toric variety. So we have some z to the r grading, the z to the r graded ring, right? And there's a theorem that's very recent. Right, it first appeared on the archive just over 2 years ago, but it appeared last year in 24 in print. And that's that if I have y inside of x, a normal subvariety, so closed, then there exists one of these virtual resolutions of S mod IY of length equal to the codimension in x of y, right? In particular, that's less than or equal to the dimension of x. Okay, fabulous. So this gives us, right, for the virtual Hilbert syzygy theorem. That we have in this setting. And in fact, right here, I've only stated it for things that look like S mod IY. But in fact, you can use this to, you can use what they did to get this for any module in this setting. Okay, question? No. Yeah, it doesn't have to be irreducible is a question. Just in this case, the normal ones are what we need. But here, once you have that, you can get this dimension bound on length for any module's resolution. Okay, cool, right? This was great. So when we first started looking at virtual resolutions, so we being me, Daniel Ehrman, and Greg Smith, we were able to prove this just for products of projective spaces, but we didn't know how to do it in general. These folks are not commutative algebraists. This is kind of cool. They are mirror symmetry people who do a lot of symplectic geometry. They were doing something totally different, and their methods happened upon this result. So now several commutative algebraists have been talking with these folks and trying to learn their techniques. And in the process, we have figured out a way to produce their resolutions using commutative algebra only. So that is what I want to tell you about now. And to do so, we need to go way back in the Wayback Machine to like 30 years ago. Not so way back. I was alive then. Maybe some of you weren't. But we're going to go back to a construction of Bayer and Sturmfels. But to do that, I'm going to use your Taylor resolution from last week to kind of motivate how their construction works. Okay. So Claudia told you about the Taylor resolution last week, and she showed it to you in terms of exterior powers of a free module. Right. So this is just the Cazul complex on 3 variables, our 3 variables corresponding to P2. And I want to kind of look at this and draw a picture to go with this. Okay, so I'm going to draw a triangle. This is a simplex in general for Taylor resolution. Okay, Taylor resolutions, you always draw a simplex for this picture. And I'm going to label the vertices with my variables. All right. And now I'm going to label the edges with, well, all faces, so the edges and the middle, with the least common multiples of all the edges of lower dimensional faces. Okay, so least common multiple here is just x0, x2, here x1, x2, and x0, x2. Least common multiples aren't very interesting when everything is relatively prime. That's fine. Here, though, it's a little more interesting. Now, I don't want to duplicate anything, so I just get the product of the variables. Okay, next, I'm going to fix an orientation. I believe I did this. You just have to make a choice so that you can use signs. And the real thing here is that if you've taken algebraic topology, I'm really thinking about the underlying chain complex for this simplex. And like, if I erased all the labels and just use ones and minus ones, that would be what I was doing. If that doesn't make sense to you, don't worry. You don't need to know it for the rest of the talk. All right, so now I need to do something else. I'm going to draw arrows from each face to the face 1 dimension down. So I have from the middle, I have 3 edges, and then from the edges, right, from this edge, I have a map to each vertex. And then I'm going to use my orientation, whether I'm with the orientation or against it, to assign a plus or a minus. Okay, so excuse me, as I look this way, this going around matches this, so this gets a plus. Here, this goes against, so it gets a minus. And here it goes with, so it gets a plus. And then here, right, the front side of my arrow always gets a plus, and this side gets a minus. So front side, minus side, front side, minus side. All right, now I go through and I'm going to look at my labels, right? And this is something Claudia actually told you about in a different form, was that to get these maps, you're looking at dividing these monomial labels. So here, I'm going to take x0, x1, x2 divided by this label, x1, x2. So I get an x0. Here, I take this divided by this, so x1 is left. And then here, x2 is left. And then similarly, along this edge, x1 divided by x2, or x1, x2 divided by x2 gives me an x1, x2, here, x0, x2, 1, 0. Okay. All right, so now I just need to line things up, and you'll see that the pink things are exactly the things in the matrices here. Okay, so let's see. So my vertices, right, are in this order in terms of ordered bases here. All right, and now for this module, I'm looking at the edges, and I want the x1, x0. So that's this. So this is the first edge here, and then the second edge has x2 and x0. This is the second edge, and this is the third edge. Okay, so if we look at this first column, that means I'm looking at the first edge. If I map to the first vertex, I have a minus x1, right? So first edge to first vertex is this first thing here, right? Think my matrices. This is edge 1, edge 2, and edge 3. And this is the vertex for x0, the vertex for x1, the vertex for x2. So I'm going from edge 1 to this v0. I have a minus x1 right here. To get to the second vertex, I have a plus x0. And then there is no map from this edge to this vertex. So that was a 0. And then I just do that for all of them. And then this last one, I'm going from the 2-dimensional face to the 3 edges. And that's my in order, right? Again, 1, 2, 3. I have x2, x1, minus x0. Okay? This is like an exercise in bookkeeping. This is our easy example for the day. So let's get it more complicated now. But let me explain what's happening to hopefully illuminate this and tie it back to what Claudia told you. Okay, so we're starting with some oriented regular cell complex. Ours will always be polyhedral, right? If this doesn't mean anything to you, just think polytope for now. And the orientation is kept track of by a map epsilon. Right, so this gives us signs. Right, this is the assignments of pluses and minuses I did here. And I have this. And now I want a monomial label M sub f on a face f and x such that they satisfy divisibility. All right. This way, when I do successive division, I get something that lands in my ring. And let's say here now, might as well use C still. Okay. So these are monomials in S. Actually, well, this is fine for now. Then what we have is a cellular complex. Oh, sorry, I'm going to change these names or I'm going to get in trouble here. Let's call these faces sigma. I apologize. Otherwise, I have F's in 2 places. Okay, the cellular complex supported on X for this M sub sigma labeling is the following. Okay, so I'm going to call it F sub X and all right, so I'm going to take direct sum over all my faces, and I'm going to use my faces as my bases for my free module. And this sigma then is in homological degree, dimension of sigma plus 1. Okay, so I've written down the entire complex as a direct sum. But really, it's a direct sum of things in a bunch of different degrees, right? So in homological degree 0, I have the empty set. Or sorry, no, I said 0. Yeah. In homological degree 1, I have my vertices. Homological degree 2, one-dimensional faces, and so forth. Okay, just like we saw here. All right, and I need to tell you the differential. So I'm just going to tell you the differential on bases because everything is an S module structure, and so that's all you need to know. Okay, so all right, so first I'm going to use my sine function. This will be 0 unless sigma prime is contained in sigma. And then it will be a plus or minus 1 if there is a containment. And the plus or minus 1 is according to my orientation. And then I have my successive division. And then that lands me in homological degree 1 less at sigma prime, right? Because these will only beep if sigma prime went down 1 dimension from sigma. Okay, so this is, Claudia gave this to you in slightly different language, but it was exactly this for the Taylor resolution. And now, and that was when X was a simplex. Now we're saying, in fact, this formula works, you know, in much more generality. You can write down in terms of being a complex, right? So this kind of forces things to be a complex. And then the question is, when is it a resolution? Okay, and Bayer and Sternfels told us what that was. Let me write that down. Yes. We can sum over all sigma prime. It's enough to sum over the ones contained in sigma, but if we sum over all of them, we don't lose anything because then these are 0.
Oh, okay, so the sign is 0.
Yeah. Exactly. Okay, so this is going to be a free resolution if and only if okay, so this is a bit of a mysterious statement, and we don't actually need it. I just want you to know that this exists. All right, so if you look at the Miller-Sternfels combinatorial commutative algebra book, they have like a whole chapter on this. So the idea is that to get a resolution, you have a topological condition on parts of X. So in particular, you're looking at the monomial labels of X, and you want the monomials whose exponents pairwise are less than or equal to any fixed vector. And you want those to essentially be contractible, right? Acyclic just means, right, like no reduced homology, right? So there is a topological condition that kind of says everything, the labels are like close enough together, given anything, that nothing bad goes wrong, and then you get a resolution, okay? And this happens a lot of the time. In particular, it does happen for our example there. And I have another example that I put up ahead of time. Yeah, it's big. I put it up just so you could see another one in action. That's pretty. Okay, yeah, so grab a picture of it. Don't try to copy it down. Just grab a picture if you want one. All right, so here we have a hexagon. So we have 6 vertices. And I started kind of at where the right side of the positive side of an x-axis would be, a squared c. And then if you read counterclockwise around, you get on the vertices the generators in the order that's listed at the top. Right, so a squared c is here, then a squared b, ab squared, and so forth. Okay, and that's the order that I'm writing the first differential in. And then I just went through and I did LCMs for each of these labels so that I knew I had this division. And then, and similarly here, and then I just did this divided by this at each stage, right? So my AB is this divided by this. Okay, and then you just start going through. So for this, I think my edges, yeah, did I write down the order my edges were in? I did. So my first edge is this one, and then a squared BC. Yeah, and then I went around counterclockwise. Okay, so in terms of the bases that go along the top here, and then along this one as well, that's the order for these. So in particular, if you look at this first column, okay, if I'm looking at this edge to map to my first vertex here, the one that goes here, I get a C. And then this was my very last vertex as I went around. and I got a minus A. And so that's at the end. Okay, and then as I keep moving around, I get this nice strip through the diagonal of the matrix. All right, so this is a procedure we can do. And when it's nice enough, we get a resolution. Yes, question. So you're saying, so in the Taylor case, yeah, you can go either direction. You can like cook up this picture from the resolution or vice versa. In general, what I want to focus on now is really starting from the picture and then trying to use it to make a resolution. And then the question is like, is it a resolution? And that theorem tells us a criterion for when it is. Oh, sorry, and that should be a not an if and only. Wait a minute. I think oh no, if and only if, I'm right. Okay, yeah, that's fine. Otherwise you have an obstruction, so. All right. Oh, yes.
Sorry, this might be silly, but earlier when we were over there,
Mhm.
you said that, and then I might be misremembering, you said that the other resolution comes from,
Yeah, Taylor resolution is always supported on a simplex.
But is this guy that we just went to the hexagon, this is not a simplex?
Not a simplex. So we're moving beyond simplices to like more general things. And so in particular, we're going to focus on kind of this polytope idea for a second. I'm about to go push it a little bit further too. Okay. All right. Because what we really want to resolve are these things, right? These equations are not monomial equations. So we can't just use this procedure and proceed. But it turns out that it's not so bad. Okay, we can still do a lot. All right, so let's look at some examples. Okay. This is going to be a big example for us today. We're just going to look at the identity point in P2, meaning all ones. Okay, the defining equation. Right, this looks a whole lot like things Elena was talking about today, although now we're back in just P2, not products. Right. And we're in our standard grading. Good. Okay, so resolution here is just the Kazoo complex on two things again, right? So this one, the resolution isn't so bad, but I'm about to do a much more complicated version and I'll explain why it's better in some, because it's generalizable, okay? So I'm just gonna write this down. So I have okay, so that's our resolution there. Let me show you, all right, in particular, yes, I'll point out this identity point into P2 already is a normal subvariety embedded into a simplicial torque variety. Maybe not a super exciting one, but it does fit that bill. Okay, here's a more interesting one. We saw it on Monday. It's the twisted cubic in a different guise. So here I want to think about using the Veronese embedding. Almost. So yeah, here we go. Okay. And what is the curve? Right, so remember we had minors. Why did I switch to Y's? I don't know. Let me just give you. There we go. Okay. And in general, we're going to get something called a lattice ideal. Okay, so if I start with an L inside of Z to the N, right? When I say lattice, I just mean that L is a subgroup of Z to the N. And what I want to do is look at vectors in Z to the N such that when I subtract them, I land inside of that subgroup. And then I'm going to use those two vectors to give me exponents. So here X has X1, X2 through Xn, and I'm raising it to a vector. So I'm doing X1 to the A1, X2 to the A2, and so forth. Okay. All right. And I'm going to assume, okay, when this corresponds to a Y, an irreducible Y, then this ideal is prime, and it's called a toric ideal, which you may have heard about before. All right. So what are our lattices? All right, so here I have my L. It is the kernel of this matrix. Have we seen this matrix before? This was our degree matrix, right? So it turns out in this case, L is the Z span of two vectors, right? And they correspond, they're now the columns of that ray matrix. And I want to choose them so that they match what I wrote here. So that is this and okay, and if you notice now, this -1, 1, 0, I'm giving, so I'm looking at A minus B. So A is 0, 1, 0. That corresponds to X1. And the -1, so then becomes 1, 0, 0 on the other side of the binomial. And that gives me an X0. So that first column here corresponds to -1, 1, 0. And this generator corresponds to -1, 0, 1. So that, we're playing this like bookkeeping game where we just keep taking these same objects but reinterpreting them. Right. Similarly here, right, maybe I won't write them all. I'll just say this one corresponds to this vector, right? So that I have the outer two giving me 1, and these two -1s are giving me this. Okay. Maybe I'll write in general here, right? L here is the kernel of this matrix. This is how I'm thinking about things there. Okay. All right. So now what we want to do is leverage this monomial approach and try to turn it into binomials. You ready? Let's do. All right, so we're going to focus on the top board there, our identity point, right? Really simple ideal, just because you'll see. All right, so the first thing I want to do, right, I have my lattice. So L now I'm thinking of as the Z span of these two vectors. I want to give these names. So this is going to be L1. This is going to be L2. Okay. What I want to do is think about now, if I think about the real span of these two vectors, these live inside of Z3, right? So if I take their real span, though, it's a two-dimensional thing. So I now have a plane inside Z3 and I'm going to use these two basis vectors as like my standard basis. Okay, so I'm looking at this RL. What I want to do is intersect that now with taking all of my variables and setting them equal to any integer that's available. Okay, so I'm going to take that two-dimensional plane and intersect it with my three coordinate axes. So that's going to take my two-dimensional plane and cut out a bunch of lines in it, right? In particular, 3 lines that slide around for every integer value. All right, so here's what this looks like. I'll do my best to draw straight on the board. I want to give myself space too. Okay.
By all those lines, for all lines.
Yes. So let me start drawing the picture and then I'll try to explain why this is the right picture in this example. Okay. So this is going to be my origin. Remember, this is in Z3, so this is 0, 0, 0. This is L1. This is L2. Okay, so this point is 2 times L1. This point is L1 plus L2. Like I'm literally just adding, using these as my standard basis, right? And I'm writing now these intersection points are my like integer lattice coordinates. Okay. So why should this be right? Well, think about if we look at L1 now. Okay, L1, the line L1 lives on is going to have third coordinate 0. So this line corresponds to x3 equals 0. Right? This is x3 equals 1. And oh, look, L2 has first coordinate or third coordinate 1. I should say, oh, sorry, x2. I'm using x0 through x2, right? Sorry, this is x2, not x3. Okay, vertical line. Look at L2. L2 has this coordinate, which is the x1 coordinate equals 0. If I go over to L1, L1 had x1 equal to 1. Okay, so hopefully now you believe me that at least the horizontal and vertical lines correspond to these x1 and x2 being integers. And then this is the other one, right? So this is now, let's see, what is it? So this is x0 equal to -1, right? Because both of these have x0 -1. And if I add the two, this is x0 equals -2. And it's going to keep getting more negative as I march to the right. It'll get positive as I march backwards. Okay. So like, would you know that? No, you have to like play with this enough and like eventually know what the pictures look like. Okay, this is certainly not obvious. All right, now I'm going to tell you how we're going to assign labels, and we're going to use monomial labels. Okay, so the next thing we're going to do here is assign. I'm actually going to assign a label. So a monomial corresponds to Z3, right, for my exponent vector. I'm going to assign a label to every point on the board, but it's going to be constant on on the pieces, the different strata you see here, whether it's a vertex, an edge, or a triangle. So I'm going to take a point P, and I'm going to send it to, oh, and I should be doing, I didn't give myself enough room. I'm going to use coordinate-wise ceiling function. Okay, so P maps to. Okay. Okay, to give me labels. All right, you ready? All right, what I'm going to do to make this easier is I'm going to erase some of my picture and just kind of zoom into this one and give you labels there. Because I don't want to redraw this whole picture either. Okay. So the origin, right? 0 maps to, 0 is going to map to 0, 0, 0, right? So that gives me x to the 0, 0, 0 is 1. Right, now let's look at L1. So L1 here. Right now I'm switching to right horizontal versus. So L1 was -1, 1, 0. Okay. So, I mean, ceilings of integers, not interesting, right? So I'm just going to get L1 mapping to L1, and I turn this into a monomial. So I have x1 over x0. And then similarly here, x2 over x0. Right? And remember, I'm doing this everywhere on the board. So in particular, let's like try, oh, let's do this one is L1 plus L2. So now I have -2, 1, 1. So that. All right, that takes care of the integer points. Now I have to worry about the edges. Okay, so let's look here. So if I do 1/2 here, now this is interesting, right? Now I have the ceiling of -1/2 is 0. The ceiling of 1 is 1. Oh. Okay, so now I'm getting 0, 1, 0. So I'm going to write an x1 here. And it turns out that was for 1/2. If I do anything on this edge, I will get those same vectors. Okay, that's the magic of this map. Right, similarly here, if I do 1/2 of L2, I get x2. Now I'll start writing things down. So same procedure, but you don't want to, we don't want to do this all day, so. Let's see, okay. And then this edge. Right, and then I still have to label these two. So if I pick any interior point, here I get 1x2, here I get that. All right, so now we play the same game. Let's orient, and I'm orienting everything. I'm going to orient uniformly everywhere. Here, 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 and here. Now I draw my maps. Oh. Yes. Yes, that's going to affect my signs.
Okay.
Yeah, so it's okay that they don't match. The point is that it changes what my function is. Thank you. Clarifying. All right, here I have this, I have this, this. Oh, and this definitely it should have an x0 on it. No, it should not. Wait, what did I do? Oh, that's why. Yes, good. Okay, this is right. All right, so if I did my signs right, these all get pluses, minus, plus. Plus, minus. Minus, minus. Okay, so this is the kind of game we're playing. Oh, I didn't write these. Okay, and then I'll just, now I do the same thing. that I have on that board where I'm going to do divide, big label divided by small label. But now I don't just have monomials, I have Laurent monomials, but that's okay. This division still works. And magically, I chose my map so that I'm always going to land back in the polynomial ring when I do the division. Okay. Okay, I think I got, nope. These are just one. Okay, that's all the labels I'm going to fill in for now. All right, so wouldn't it be nice if we could somehow now turn this into the resolution of our point, right? I see my equations for my point are actually sitting in that triangle, right? And they can. Let me tell you what's happening. All right. All right. Instead of my monomial assignment now, I'm going to start with my monomial assignment coming from this, right? And, right, so in particular now, it's important that there are some special conditions on psi, right? The ceiling function is one of them. The ceiling function is a psi that works in general in this setup always, okay? That's essentially the only one we'll work with. You'll see if you go to the advanced exercises, it gets slightly more complicated, but it only involves ceilings and floors. In particular, it has to be constant on these different strata, these pieces, and satisfy the divisibility. Okay. So here I'm going to take a p. It's going to give me a psi of p, which then I'll use to write down a monomial that I'll call m sub psi of p. Okay. All right. Yes, yeah, sorry, I should say that. I meant to add here. Now this is in T, where T is. Now we're not polynomials. Great, thank you. Okay, so the cellular complex now that we're going to call F psi is going to come from, I'm going to call capital psi the stratification that goes with this. And I'll put that here. Psi is constant on strata, so I can write this. Guess I can leave my sigmas in now my pieces. So here, I'll say here. From all these IJs. Okay. And the only thing I need to change now are these. Okay. All right. So with this setup, the Bayer-Sternfels theorem still works, where I put psi of b instead of, or instead of b. Okay, so I get a criterion for how to understand these resolutions. But now what I need to be able to do is somehow collapse this into the thing I actually want, which is a resolution of the binomial thing. And so to do that, I'm going to go mod L, mod this lattice. If I do that, I'm left with only this picture. But now this picture is like a real 2 torus, right? And that's the magic here. A question?
Sorry, what's the object?
We're just changing to be like, yeah, it's like, it's, if you like, it's this. Or you could think of this as being like the pieces of the stratification. But I think this is actually, I know this is really what you want to think about because you're taking all of the chunks of X that satisfy that. So it really looks the same. I'm just adding a psi everywhere. Okay, so sorry, thank you. Yeah, X here should be, yeah, X is this RL. Yeah, or if you like, intersected with all these. Depends if you're thinking of X as the underlying topological space or the stratified space, like the CW space. I like to think of it with this as well, but neither here nor there for what I want to say. All right. So I'm going to write down some modules that make the magic work. And I'm not going to say a lot about them because we don't have a ton of time. I'm going to throw in a whole nother set of n variables that I call z. Right? And they can have positive or negative exponents. Right? This surjects onto S, right, where I just take this and I go mod z to the a minus 1 over all of the a's. Right? If I just kill them off, if I set these all equal to 1, I just recover S. All right, and of course, my lattice ideal I started with lived here. Okay. All right. If I take just the module spanned by the vertices you see here in this picture across the entire plane, and then I tensor over this with this, I get S mod IL. Okay, so this is something Bayer and Sternfeld showed in this case. And really what's happening is in the picture, we're going mod L. Okay, so going mod L essentially gives us S mod IL when like all our vertices landed at integer points. Okay, but they don't have to always land at integer points. And that's an extra reason the ceiling function is needed, so that vertices especially are getting honest monomial labels. Okay. All right, maybe I won't erase the beautiful picture. I'll instead go here. All right, and so I want to give you the punchline. I did erase it. So the Hamlin-Hicks-Lazarev theorem, remember, it told us that there was a resolution for any closed subvariety of our torque variety, in particular this identity point in P2, but this works much more generally. But the way that they wrote their paper, we didn't know exactly what the resolution looked like in the commutative algebra setting. And we didn't know, in particular, it turned out that we knew it was acyclic, but we didn't know what module it was resolving over the Cox ring. Okay, so that is what we can do now. So this is a paper that'll come very soon on the archive. Okay, so Lauren was sick and is now here with us. So Lauren is in the back, which is awesome. This is Greg Smith of the Smith, and this is Jay Yang, who was here last week. Greg was here last week too, right? We did a collaborator switch this week. Okay, so if I take now what I called F psi, I did a beautiful F, we'll keep it that way. If I tensor it over S with S bracket L, this equals, up to sheafification, the Hamlin-Hicks-Lazarev resolution. And it's a resolution of S mod IY. And maybe to finish up then, the last thing I want to do for you is just draw out this picture. Right here. Okay, so what's going to happen is I'm now going to have, right, still have a single vertex now because this is a torus. I have, I'm not going to write out the grading. Oh no, this is just my one. Right, I have 3 edges, 1, 2, 3, because these two and these two identify. And then I have two triangles, right? So this is a partial 1 and that's a partial 2. And now to fill these in, I just go through and I look like I've been looking, right? So I'm just literally say, okay, if this is my first edge, I definitely didn't do this right. This should be x0. There we go. So like for this edge, I'm going to get x1 minus x0 in that part of the differential. Did I mess something up? Wait, where? Minus 1, minus 1, minus 1? Which one? Oh, that's right. Thank you. This should be like this, right? There we go. Yes, because this was these are all ones. Sorry about that. It's right here. I just didn't look at my notes and I'm going fast. Okay, so for partial 1, I have 3 binomials, x1 minus x0, x0 minus x2, and x2 minus x1. So earlier we saw these two were the 2 that we used in our resolution. We have an extra one, and that's why we're going to have this extra identity map coming from this. Right, so this partial 2 map, here we just, for this one, we just get our variables. And then I have minus 1s. Right, so we can just minimize away that extra minus 1. Right, this is a redundant, and that kills off one of our generators, that's fine. So we can minimize this to get back to the resolution we started with. Why is this not so bad? Well, now we have something cellular. Right, before we had a minimal free resolution, but like we were reliant on something like Macaulay 2 to go grab that resolution. Now we have a procedure that works in general for any of these closed subvarieties and gives us a resolution that has extra topological structure that we can now try to exploit to understand our modules better. So like, I'll just end by saying kind of the beauty of this multigraded setting now is that we get extra combinatorics from the multigrading that gives us new tools to attack the problems we're interested in. All right, thank you so much.